In World War II, there was a heating technology so efficient that energy companies spent decades trying to bury it. Not because it didn't work, but because it worked too well. Soldiers in frozen bunkers were staying warmer than officers in heated barracks, using nothing but a handful of twigs. And they were doing it with a stove design that turned basic physics into the heat output of a modern propane heater. By 1945, over 60% of frontline soldiers had built their own versions. But the moment peace was declared, the designs disappeared from military manuals. Patents were filed and buried, and engineers who tried to commercialize it were quietly shut down. Why? Because if people realized they could heat their homes using nothing but fallen branches, the entire fuel industry would collapse overnight. Today, you pay hundreds or thousands per year to heat your home. But the technology that could eliminate those bills entirely still exists, buried in wartime archives and forgotten military documents. In this video, we're uncovering the World War II rocket stove design that was deliberately hidden from history. The design that achieves 90% thermal efficiency compared to modern propane heaters at 60 to 70%. And most importantly, how to build one yourself using basic materials and measurements that actually work. By the end, you'll understand the exact physics that make it superior, and how to never pay for heating fuel again. Number 1. The core physics of rocket stove efficiency. The fundamental difference between a rocket stove and conventional heaters isn't complexity. It's combustion temperature and airflow design. A standard wood fire burns at 600 to 800 degrees Fahrenheit. At this temperature, wood releases combustible gases, but those gases escape as smoke before they can ignite. That smoke represents wasted energy, up to 40% of the fuel's potential heat, literally floating away unused. A rocket stove solves this through a vertical combustion chamber that reaches temperatures above 1200 degrees Fahrenheit. At this temperature, something critical happens. The gases released from burning wood spontaneously ignite in what's called secondary combustion. You're not just burning wood, you're burning the smoke itself. This is achieved through 3 specific design elements working together. First, a horizontal fuel feed tube forces wood to burn from one end only, creating a controlled, concentrated flame. Second, a vertical combustion chamber positioned directly above the feed creates an intense heat zone where temperatures spike. Third, a tall insulated chimney creates powerful draft that pulls air through the system at high velocity. The result is measurable. Independent tests during World War II showed that 500 grams of wood in a rocket stove produced the same usable heat as 1,800 grams in an open fire. That's 3.6 times more energy from the same fuel. Modern propane heaters, which lose significant heat through venting and incomplete combustion, typically achieve only 60 to 70% efficiency. A properly built rocket stove reaches 85 to 90%. What made this design revolutionary wasn't just the efficiency, it was the simplicity. No moving parts, no electrical components, no precision engineering required. Just metal tubes positioned at specific angles, with correct dimensional ratios. Because when you understand the physics, the materials become almost irrelevant. Number 2. The critical dimensional ratios. During the war, soldiers discovered that rocket stoves only worked when specific proportions were maintained. Get the measurements wrong, and you'd have a smoky, inefficient fire. Get them right, and you'd have a heating system that defied conventional understanding. The first critical ratio is the fuel feed diameter to combustion chamber diameter. This must be approximately 1 to 2. If your fuel feed tube is 3 inches in diameter, your combustion chamber must be 6 inches. This ratio creates the correct air-to-fuel mixture. Too narrow, and you starve the fire of oxygen. Too wide, and you lose the concentrated flame needed for high temperatures. The second ratio is combustion chamber height to diameter. This should be 1 to 1, or 1.5 to 1. A 6-inch diameter chamber should be 6 to 9 inches tall. This gives the flame enough vertical space to fully develop before entering the heat riser, but not so much space that heat dissipates before reaching peak temperature. The third critical measurement is heat riser height. This should be 3 to 4 times the height of the combustion chamber. If your chamber is 8 inches tall, your heat riser should be 24 to 32 inches. This height creates the draft velocity needed to pull air through the system. Shorter, and the draft is weak. Taller, and you actually lose efficiency as too much heat escapes before it can be captured. The feed tube angle is equally important. It should enter the combustion chamber at 15 to 20 degrees upward from horizontal. This forces flames upward into the combustion zone rather than back toward the fuel entrance. Military field manuals from the Eastern Front specified exactly 18 degrees as optimal, though 15 to 20 degrees all function adequately. Finally, the insulation gap. The combustion chamber and lower third of the heat riser must be surrounded by at least 2 to 3 inches of insulating material. This can be perlite, vermiculite, wood ash, sand, or even packed earth. The insulation forces heat upward instead of radiating outward, maintaining the high temperatures required for secondary combustion. These aren't suggestions, they're requirements. Change these ratios significantly, and the physics stop working. But maintain them, even with crude materials and rough construction, and the stove will perform as designed, because the laws of thermodynamics don't care about precision metalwork. They only care about correct proportions. Number 3. Material selection and construction methods. One of the most valuable lessons from World War II rocket stoves was that material quality mattered far less than dimensional accuracy. Soldiers built functional stoves from artillery casings, damaged vehicle parts, even flattened tin cans layered together. For the fuel feed tube, any metal pipe or tube 3 to 4 inches in diameter works. Steel is ideal because it withstands high heat, but even aluminum cans rolled and sealed can function for temporary builds. The length should be 10 to 14 inches. Longer than this, and friction reduces airflow. Shorter, and you can't fit sufficient fuel. The combustion chamber can be built from a section of larger diameter pipe, a metal can, or even a clay cylinder if properly fired. The key requirement is heat resistance. At minimum, it must withstand 1200 degrees Fahrenheit without warping or melting. Standard steel pipe, cast iron, or heavy gauge stainless steel all work well. The heat riser follows the same material requirements as the combustion chamber. However, it will experience slightly lower temperatures due to heat extraction, so even thinner materials function here. Many World War II designs used sheet metal rolled into cylinders and riveted or welded. For the outer shell that holds insulation, almost anything works. 5-gallon metal buckets, square metal containers, even masonry blocks arranged in a square. The only requirement is that it's non-flammable and can contain loose insulation material without collapsing. The insulation itself has several options. Perlite and vermiculite are modern choices that provide excellent insulation. Wood ash, which soldiers had in abundance, works nearly as well and costs nothing. Dry sand provides moderate insulation. Even packed earth will function, though it's less efficient than other options. Assembly is straightforward. Cut a hole in the combustion chamber near the bottom, sized to fit the fuel feed tube. Insert the feed tube at the correct 15 to 20 degree upward angle. Seal the joint with furnace cement, high-temperature epoxy, or even mud mixed with clay. Position this assembly inside the outer shell. Fill the gap with insulation, packing it firmly but not compressing it so tightly that air spaces disappear. The total material cost, if purchased new, runs $20 to $50 depending on what you already have. Using scrap materials, the cost is zero. And unlike modern heaters that require specialized parts and professional installation, a rocket stove can be built by anyone with basic tools and the ability to cut metal. Number 4. Fuel flexibility and combustion science. Modern heating systems are fuel-specific by design. Natural gas heaters require natural gas. Propane heaters require propane. Pellet stoves require manufactured pellets. This specialization creates dependency and recurring costs. Rocket stoves operate on a different principle entirely. The extreme combustion temperatures achieved in a properly built rocket stove mean that almost any dry organic material will burn completely. Soldiers used whatever was available. In European forests, they burned twigs and small branches. In North African deserts, they burned dried camel dung and scrub brush. In Pacific islands, they burned bamboo and coconut husks. The key factor isn't the type of fuel, it's the moisture content and size. Fuel should be dry, or at least under 20% moisture content. At rocket stove temperatures, even slightly damp wood will burn, but wet wood wastes energy, evaporating water before combustion can occur. Fuel pieces should be no thicker than 2 to 3 inches in diameter to fit through the feed tube and burn completely. This accepts an enormous range of materials: wood scraps from construction or yard waste, dried corn stalks or agricultural waste, cardboard and paper products, dried animal manure, which has been used as fuel for thousands of years. Even processed materials like wooden pallets or shipping crates work well once broken into appropriate sizes. The combustion process itself is more complete than conventional fires. In a normal campfire or wood stove, combustion is incomplete. You see black smoke, which is unburned carbon particles, and creosote buildup, which is condensed unburned gases. A rocket stove, operating at peak temperature with strong airflow, burns these components. The exhaust is mostly clear with minimal particulates. This has practical advantages. First, you extract more energy from less fuel. Tests show wood consumption reduced by 70 to 80% compared to open fires for the same heat output. Second, there's no creosote buildup requiring chimney cleaning. The high temperatures burn it before it can condense. Third, the cleaner combustion produces less pollution, making it safer for indoor use with proper ventilation. The flexibility extends to fuel sources. In a grid-down scenario or fuel shortage, you're not dependent on deliveries, supply chains, or infrastructure. Any organic material that can dry and fit through the feed tube becomes potential fuel. This was critical during World War II when supply lines were constantly disrupted, and it remains valuable today for anyone seeking independence from fuel monopolies. Number 5. Heat output and thermal mass integration. A basic rocket stove produces intense heat, but that heat dissipates quickly when fuel stops burning. For continuous heating, you'd need to constantly feed fuel, which is impractical. The solution developed during World War II was thermal mass integration. Thermal mass is any material that absorbs heat and releases it slowly over time. Stone, brick, concrete, and earth all function as thermal mass. The principle is simple. Surround the hot parts of the stove with dense material. That material heats up during burning and continues radiating heat for hours after the fire goes out. The most effective placement is around the heat riser and exhaust path. Soldiers built stone or brick enclosures around their stoves, leaving the fuel feed accessible but wrapping everything else in mass. A typical design used rocks or bricks arranged with a 4 to 6 inch gap from the metal, filled with sand or smaller stones. The physics are straightforward. During a 30 to 45 minute burn, the metal components reach 800 to 1000 degrees Fahrenheit. This heat radiates into the surrounding mass. Stone and brick heat slowly, but once hot, they retain that heat for extended periods. A well-designed thermal mass system continues outputting usable heat for 6 to 10 hours after the fire extinguishes. This creates a completely different heating pattern than forced air systems. Instead of blowing hot air that quickly escapes or rises to the ceiling, thermal mass creates radiant heat that warms surfaces and people directly. It's the same principle behind heated floors and traditional masonry heaters, but achieved with simple materials and basic construction. The heat output numbers are significant. A rocket stove burning continuously can produce 15,000 to 25,000 BTUs per hour, depending on fuel feed rate. For comparison, a standard space heater outputs 5,000 to 10,000 BTUs. The difference is that the rocket stove achieves this using free fuel. A single armload of small branches, which you'd normally leave on the ground or haul to a dump, contains enough energy to heat a room for an entire day when burned in a rocket stove with thermal mass. Scaling this up, military engineers calculated that a properly designed rocket stove system with adequate thermal mass could heat a 20 by 20 foot space to comfortable temperatures in winter climates, using approximately 1/10 the wood of a conventional stove. In practical terms, this meant soldiers could maintain warm quarters using fuel gathered in 30 minutes rather than hours of wood chopping and hauling. Number 6. The suppression of commercial development. After World War II, multiple attempts were made to bring rocket stove technology into commercial production for civilian use. Every attempt was blocked through a combination of regulatory barriers, patent manipulation, and industry pressure. The documented history is revealing. Between 1946 and 1955, at least 17 patents were filed for high-efficiency wood-burning heaters based on rocket stove principles. Of these, only 2 were approved, and both included design modifications that deliberately reduced efficiency to levels comparable with conventional wood stoves. Building codes presented another barrier. By the 1960s, most municipal codes required heating appliances to be UL listed or carry equivalent certification. The testing and certification process cost tens of thousands of dollars, required extensive documentation, and often took years. Small manufacturers couldn't afford it, and large manufacturers had no incentive to pursue technology that would cannibalize their existing product lines. Insurance companies added another layer. Homes with non-approved heating systems were denied coverage or charged prohibitive premiums. This effectively prevented adoption, even among people willing to build their own systems. The narrative shifted from highly efficient to primitive and unsafe. Trade publications began publishing articles warning about rocket stoves, usually citing risks that applied equally to conventional wood stoves, but were presented as unique problems. The message was clear: stick with approved, purchased equipment from established manufacturers. What's notable is what wasn't argued. Efficiency numbers weren't disputed because they were measurable and undeniable. Instead, the focus shifted to regulations, safety concerns, and the need for proper equipment. The underlying message: it's not that rocket stoves don't work, it's that you shouldn't be allowed to use them. By the 1970s, the knowledge had largely disappeared from mainstream discussion. It survived only in niche communities, military surplus documentation, and among older veterans who remembered building them during the war. The technology that could have eliminated home heating costs for millions was successfully buried under layers of regulation, industry pressure, and manufactured doubt. Number 7. Modern resurrection and performance data. Starting around 2005, rocket stove technology began re-emerging through online communities, homesteading forums, and off-grid builders sharing designs. This grassroots resurrection provided an opportunity for rigorous modern testing using equipment unavailable during World War II. Thermal imaging cameras revealed the temperature distributions. Properly built rocket stoves maintain combustion chamber temperatures of 1200 to 1400 degrees Fahrenheit, with heat riser temperatures of 900 to 1100 degrees Fahrenheit. Exhaust temperatures at the top of the riser measure 400 to 600 degrees Fahrenheit, indicating efficient heat extraction. Emissions testing showed dramatic improvements over conventional wood burning. A rocket stove produces 80 to 90% less particulate matter than an open fire and 60 to 70% less than EPA-certified wood stoves. Carbon monoxide emissions are similarly reduced due to more complete combustion. Fuel consumption measurements confirmed World War II-era claims. Controlled tests burning identical wood quantities showed rocket stoves producing 3 to 4 times more usable heat than open fires and 2 to 3 times more than conventional wood stoves. In practical terms, this means heating a home through winter using 1 to 2 cords of wood instead of the 6 to 8 cords typical for conventional stoves. Modern builders have refined the basic design with improvements. Better insulation materials increase efficiency. Welded construction replaces makeshift seals. And some designs incorporate heat exchangers, water heating loops, or cooking surfaces. But the core physics remain unchanged from the World War II originals. Cost analyses show stark differences from commercial options. A DIY rocket stove costs $30 to $100 in materials. A comparable BTU-rated propane heater costs $300 to $800, plus $500 to $2,000 per year in fuel costs. Natural gas systems require professional installation at $2,000 to $5,000, plus ongoing monthly bills. The rocket stove pays for itself immediately and requires zero fuel costs if free wood is available. The data demonstrates what should be obvious. Rocket stove technology isn't historical curiosity or survival gimmick. It's demonstrably superior heating technology that was deliberately suppressed because it eliminated recurring revenue streams. The physics haven't changed. The measurements still work. And despite decades of suppression, the knowledge survived because the need never disappeared. Every winter, millions of people pay for heat that nature provides freely. They're told it requires purchased fuel, professional equipment, and monthly bills. But during the worst war in human history, ordinary people proved otherwise. They built systems that outperformed what were sold today, using scrap materials and wartime ingenuity. The choice remains. You can continue depending on systems designed for profit extraction, or you can build something that works by the laws of physics rather than the rules of commerce. The rocket stove doesn't care about your location, your budget, or whether utility companies approve. It works because thermodynamics are universal, and combustion follows predictable patterns. Master those principles, and you've mastered independent heating. If you believe knowledge should be free, if you question why simple solutions to expensive problems stay buried, if you want capability rather than dependence, then understanding this technology isn't optional. It's essential. Subscribe now. Learn what they don't profit from teaching, and become someone who controls their own comfort without permission or payment.